The following demonstration was conducted in the Adrenaline testbed to validate the dynamic provisioning capabilities of the seasoned MBoSDM architecture and the integration of control and data plane components. During initialization, the SDN controller establishes secure sessions with every device in the scenario. It performs a comprehensive discovery process. It retrieves device capabilities, enumerates all available components and ports, and identifies supported operational modes. This data is used to build an accurate, real-time topology and resource inventory. With the help of the graphical user interface, a network map is showed. The network is populated with different device icons representing the various nodes. The controller's interface now visualizes the complete discovered topology. The assessed scenario incorporates both real hardware elements, including the seasoned node prototype, ROADM, and SBVT transmitter and receiver nodes, and additionally, virtual nodes to emulate complex network topologies. Selecting a node reveals its specific attributes. Detailed information, including operational state, supported modes, and visual maps of resources, is now available. This confirms the controller has successfully retrieved all necessary data from the hardware. With a full inventory of resources and capabilities confirmed, the system is now ready for accurate path computation and dynamic service provisioning. The first use case involves setting up an SDM service between two virtual nodes, traversing the physical MBoSDM node. This process demonstrates the controller's ability to compute the route, allocate resources at the core level, and configure the necessary cross-connections dynamically. Having completed the discovery phase, the controller already possesses an accurate, real-time view of the entire topology, including all available ports, cores, and spectrum resources. The workflow begins with the creation of an SDM service between the two virtual nodes through the controller's interface. The operator defines key service parameters, name, qualifier, ingress and egress points, function, and in this case number of cores. The SDN controller now computes the optimal route and allocates the specific available cores required to meet the service's demands. With the path determined, the controller sends configuration instructions directly to the physical MBoSDM node. These messages, structured via a specific data model, configure the precise cross-connections at the core level. They specify input and output ports, input and output cores, and all necessary parameters for SDM switching. The system logs confirm a successful configuration update, with a positive response indicating the edit was applied without error. The SDM service is now active and confirmed. The interface reflects the selected end-to-end connection and illustrates the final resource allocation, showing the specific cores assigned to this connection along the network links. These panels provide a visual confirmation of how spectrum and spatial resources are now distributed, confirming the physical node is actively performing the core switching as instructed. The workflow concludes with the successful decommissioning and deletion of the SDM service. Now, a second service is established, a multiband FlexiGrid service designed to demonstrate multiband operation. In this scenario, the controller provisions a FlexGrid connection that spans from a SBVT transmitter node through the season node and a ROADM supporting both C and L bands to a SBVT receiver node. The workflow begins when the controller receives a service creation request for this multiband connection. As the first use case, the operator defines key service parameters, name, qualifier, ingress and egress points, function, and in this second use case bandwidth. As before, the SDN controller computes the optimal route and allocates the specific bandwidth required to meet the service's demands. The controller then establishes the service by sending configuration messages to the devices involved. The selected route crosses a ROADM, the so-called Node 4, which includes support for C plus L bands. The season node is configured to establish multi-band cross-connections. Simultaneously, the SBVT transmitter and SBVT receiver nodes are configured with specific parameters such as frequency, output power, and operational mode. These configurations enable the creation of a multi-band optical channel that spans both C and L bands, leveraging the extended spectral resources for higher capacity. After successful configuration, the multiband flow is transmitted across the provision path. The L-band component is successfully received at the destination node, validating the multiband capability of the system. Performance metrics, such as signal-to-noise ratio and bit error rate, are collected and visualized. Following confirmation, the operator initiates service termination, resulting in the deletion of the SDM connection and the release of all allocated spatial resources.